recording. This is Math 111Z, and this is section 2.4. All right. And I'm going to shut this door so we don't have any background noise. So this chapter is on graphs of functions. And I think if you think back to when you were in the 6th or 7th grade, if you had if you needed to graph a set of points, like S equals the set of points 2, 1, 3, 1, 4, 2. This is a function because for exactly every one x there is a unique y. We would just graph. Of course, the x's come first on the x-axis, the y-axis. We would graph 2, 1 as a point, 3, 1 as a point, and then 4, 2 as a point. So that would be the graph of that function. We also, at some point, talked about graphing functions that were given in tables. So if we had 1, 2, 2, 4, 3, 6, 4, 8, we would graph 1, 2, 2, 4, 3, 6, 4, 8, and that would be the graph of this function. Then we started talking about how do you graph functions that are in equation form. And let's say we were looking at the graph, a linear graph of 3x plus 5. There's so many different ways to do this. One way to do this we learned really early on, which was to plug in points for x and y. So if x was 0, y was 5. If x was 1, y was 13 halves. If x was 2, y was 8. If x was 4, y was 11, and so on. So we would plug in points. Zero, 5, 1, 13 halves, which is 6.5. 2 is 8. 4 was 11. And you would plot those points, and then you would kind of draw your line in, connecting the points that you had plotted. Anytime you have any linear function, especially in the graphing form y equals mx plus b, where m is your slope and b is your y-intercept, then let's say I have y equals 2x plus 6. You would go to your y-intercept, which is 6, and then you would know your slope is 2, which is the same as 2 over 1, which means you'd go up 2 over 1, up 2 over 1, and you would get this line formed right there. Now, the more you know about what your parent functions are and look like, then the easier it is to graph these types of functions. So let's say, what does a quadratic look like? All quadratics look like some form of a parabola shifted to wherever the vertex is, and flipped over and stretched based on whatever your letter A is. So quadratics in graphing form is the same as being in vertex form. The form y equals a times x minus h squared plus k. It's also kind of completing the square form. In your quadratic, your vertex becomes the point HK, and then your A becomes kind of your stretch. So if A is like 3, excuse me, Your first one, you would go over 1, up 3, over 1, up 3. Your second one, you would go over 2. Normally, you'd go up 4, but if A is 3, you would go up 12, and this would give you a very steep stretch going up this way. If you want to think about from HK, your steps over versus up, over and up, if you go over 1 in each direction, you go up whatever A is. If A is negative, you go down. If you go over 2 in each direction, you go 4 times A. If you go over 3 in each direction, you go 9 times A. Notice this is a squaring function because it's squared, it's a quadratic. You go over 4, this would be 16 times A. Go over 5, it'd be 25 times whatever A is. So that is how you can easily graph a quadratic equation. I'll do an example that they gave in the book. They asked you to graph f of x equals x squared minus 2. Notice if I put this in vertex form, this is f of x equals a is 1, because the 1 in front of the x squared, x minus 0 squared, because there's no b term, and then minus 2. So my h is 0, my k is negative 2. My a is 1. So from here, I go down to my vertex at 0, negative 2. And then as I said in that last chart, I go up, over 1, up 1, over 1, up 1, go over 2, up 4. 1, 2, 1, 2, 3, 4. 1, 2, 1, 2, 3, 4. And I get a parabola that looks like this. Now, while you won't be able to use it for your exams, Desmos is an excellent graphing tool that you can check your work at. So if you go to your free graphing tool, Desmos, and if you're curious, you're having a struggle and you don't quite know how it's supposed to look, you can always go to Desmos. Other basic function families that you should kind of have an idea of what it looks like is the square root function. That's a parabola kicked on its side. You go over 1, up 1. You go over 2. Or actually over 4. Over up 2. Over 9. Square root of 9 is 3. Up 3. And I always think of this one as a Nike swoosh, kind of upside down Nike swoosh. That's how I think of it in my head. And you will also notice the domain of this. You can't square root a negative, so there's nothing over here. Like this part of the area is blank, right? It's not defined over here. The other function family you should have an idea of what it looks like is the absolute value of x. Whenever it's positive, it just kicks out itself in a positive manner. Wherever it's negative, it kicks out itself in a positive manner. So you get the V-shaped function for the absolute value of x. Again, you can always kind of put numbers in a table to kind of test this and see how it works. Graphing a piecewise function. Let's take this example here. I got x squared if x is less than 0. I have x plus 1 where x is between 0 and 3. And then I have negative 1 where x is greater than or equal to 3. So essentially what I am doing is breaking my graph into 3 distinct chunks. The first chunk when x is less than 0, so everything to the left of that dotted line. the next chunk, when x is less than 3. So between these two dotted lines, and then the last chunk, anything greater than 3. I'm going to do the last chunk first because it's the easiest to graph. That is just a line at -1. It's a constant line at -1. So if I go down here to -1, I'm filling it in at 3. I have a closed circle here, and it's going to look like that. Anything greater than, I'm sorry, did I make that sign the wrong sign from the book? I must have, because it wouldn't make sense. Yeah, this sign is wrong. There we go. And this is example 5 out of your textbook in 2.4. So anything greater than this is going to go this way. Now between this is just a line with a slope of 1 and an intercept at 1. So here at 0, and notice 0 is included, I have an intercept at 1. And then my slope is 1, so I go up 1 over 1, up 1 over 1, up 1 over 1. But this 3 is not included here. So instead of doing a closed circle, I need to make sure I do an open circle. And then I'm going to connect that line and look at like that.
What is this called?
This is a piecewise function.
So why is why your slope 1?
Because we're working with this piece right here. And this is the function f of x equals x plus 1, which you'll notice is mx plus b form, where my slope is the number in front of the x, which is 1,
Yeah.
and the b is the intercept right there.
Yeah. Okay.
Okay? So from here, now I have x squared on this piece right here, so I'm going to go back 1, up 1. Back 2, a is 1, so I'm going to go up 4. Back 3 up 9 would be up here. And you get this parabola piece that looks like here. Remember that this not includes 0, so that's an open circle there. And those are what those 3 pieces look like. Let's take another example of a piecewise function. This one's a nice, kind of fun one because both graphs are pretty easy. All right, you have -5 if x is less than or equal to 0, and 4 if x is greater than 0. And that's nice. Okay, less than 0 is -5, so I go to -5, 1, 2, 3, 4, 5 on the y. And any x that's less than or equal to 0, so solid line, goes that way. If it's greater than 0, then the value is always 4. Open circle, because there's no line under the 0, line goes that way. And we're looking at that graph right there. I believe that last week we talked about the vertical line test. And it is a test to test a function, graph, to test a graph if it's a function. So maybe I have a parabola that looks something like this. Is that a function? Well, I ask myself, can I draw a single vertical line that is going to touch this function in more than one spot? And the answer is no. No matter what vertical lines I do, I always get exactly one answer. So this would pass the vertical line test, and it would tell me that this is a function. Examples of things that don't pass the vertical line test are circles. Circles don't pass the vertical line test. Ellipses. You remember what an ellipse is? Maybe, depending on if you've had them before, they're like an oval circle. Don't pass the vertical line test. Parabolas that are y squared instead of x squared look like that. Oops. Look like that. They don't pass the vertical line test. So most of the conic sections are not going to pass the vertical line test. All right. and therefore are not functions without some sort of domain restriction. Suppose you had a graph that looks like this.
Hyperbolas wouldn't either, right?
That's correct. So here, that's my graph. Draw a vertical line, hit here, hit here, hit here, hit here, fail. It really only has to fail 1 point to fail the function test. So let's say I had a piecewise function that accidentally had both endpoints filled in. Because I could draw this single line and touch 2 points, it fails the vertical line test, and this is not a function. Okay? Let's talk about what is an intercept. An intercept is, wait for it, where it intercepts the x-axis and the y-axis. We typically refer to the intercept as the y-axis interception. We call the x-axis, where it intercepts the x-axis. We have other names for that. We do call it the x-intercept, but there's several names for the x-axis. X-intercept, roots, zeros. Your book calls them zeros and x-intercepts. A lot of books will call them roots of the function. It is what x, like say if I'm looking at a function that looks like this, I'm asking what x's make this function equal to 0. That's the x-intercept. The y-intercept is what y do I get when I plug 0 in? The y-intercept's always a lot easier to find than the x-intercepts. We can often talk about functions, whether or not they increase or decrease. So you can have an increasing function, which means it's always climbing up, or a decreasing function where it's always going down. Right? It's like a positive slope or a negative slope of a particular function. Let's just take a quick glance at this week's homework, and I'm just going to check, or this night's homework. I'm just going to kind of run through some of those problems and see if there are anything that maybe we missed. I'm going to go to question 5 right off the bat. Okay, question 5. Okay, so it asks us to, on question 5, my question 5, says t of x, which is just the name of a function, for me is x squared on the Cartesian plane.
Yes.
All right, so at first it says,
Oh, Cartesian plane, what does that mean?
that means just your x coordinate, y,
Oh.
your regular plane. Like the Cartesian plane is named after Rene Descartes, who was a mathematician, and he is the one that came up with the rectangular grid.
Remember?
You know, like the fly thing on the ceiling.
Oh.
He was looking at the ceiling and was like, oh, that fly goes over 2, up 3. So then he came up with this idea that the point 2, 3 is over 2, up 3, and so on. He came up with the Cartesian plane, which is what our coordinate plane is. It says, choose the name of the toolkit function you graph. This is a quadratic, because it's squared, right? If I look through just the choices it gives me, it's not a cubic, which would mean a cube thing. It's not a reciprocal, which would be 1 over x. So let's go over what a cubic is. A cubic is cubed. Reciprocal is 1 over x, 1 over something. A quadratic is something squared. A linear is mx plus b. A exponential is some constant e to the bx, and a log is the natural log, some constant natural log of x kind of thing. Right? That's or log some base, but these are gonna be your general kind of toolkit of families. So then it asks for the domain of this. My domain has nothing divided on the bottom. It has no square roots, so my domain is all real numbers.
What is the range, or what is the definition of
It's
range?
the Y.
Range is the widest that can come out of this function. Is there any number that I could put in here to get a negative number out? No, so my range is gonna be only positive numbers. I can get 0 out, and then all the positive numbers will come out, but that is all. So my answer for range should look like this. My answer for domain should actually look like negative infinity to infinity, which is how I would write in interval notation all real numbers. And now it asks me to go ahead and graph this. When I'm looking at my open math, they give me some choices for graphing. They give me like a little line. They give me a parabola shape. They give me an absolute value shape. They give me a circle shape, and then they give me a point. Right? It says if any of the it did say if the range does not exist or if the domain did not exist, just leave it blank, but that's not the case. So when I graph this, I choose my parabola one. I need to pick 2 points that are on the parabola. 0, 0 I know is on my parabola, and I need to point the vertex. My vertex is at 0, 0. And then I know I need to go over 1, up 1. Or I could go over 2, up 4. And then hit submit, and I should get a green box around my graph. Okay? For the parabola. All right. Are there other, I feel like that should be pretty good for a start. I'm gonna let you guys go ahead and dig into this, my open math homework, and then as you come to questions, we can respond to those.
Okay.